Welcome back. Now I mentioned that we're going to use matrices to solve. And the first thing we use to solve a system of equations is what's called a coefficient matrix. A coefficient matrix is a linear system, is the matrix of all the coefficients aligned in columns. So each variable gets a different column. For example, this system would turn into this matrix, because notice what we are doing is we're taking all of the coefficients here and they get a corresponding spot. So notice the coefficient here, even though you don't see anything, is because it's 0 times x1. So that's why we get a 0 over in the matrix. So looking at this, you can hopefully see that if I took all the coefficients along this, that turns into a single column. And this is where it's going to get important, is we are going to deal with coefficient matrices, and then we're going to take it up a step and talk about augmented matrices. Both have a place in the class, so you need to understand the difference between the two of them. An augmented matrix is a coefficient matrix with an added column containing the constants on the right side. So this, again, notice that this portion before the solid line is the same thing as our coefficient matrix. And then we add a solid line. Also, some books and so forth use dotted lines, but almost always there is a line to differentiate between the coefficient portion and the constant portion. And then we have a column that corresponds to constants on the other side of the equal sign. We will talk later on about you can actually have several columns over here on this side. And so you can end up it's kind of like having two matrices separated by a single divider. So a coefficient matrix is the way that we kind of set up this. Then we talk about augmenting by adding those actual given constant values. Now, to do this, we're actually now going to then use what are called row operations. Now, a row operation will maintain the equivalent solution set, meaning the solutions do not change, and there's a few of them. First is replace. So I can replace any row by the sum of itself and the multiple of another row. I will demonstrate this in a second. You can think about this as adding two equations together and replacing one equation with a sum of two equations. I can switch two rows. Obviously, that wouldn't change my solution set. The rows are not fixed, so we can switch rows. Note, you cannot switch columns, just rows. Scale, I can multiply an entire row by a constant value, and it does not change it. So let's look at some examples so you can see those three. Let me go back for a second. These three operations in action. So suppose for a second that I have this system. The first thing I'm going to do is I'm going to turn it into its augmented matrix. Now we're going to take that augmented matrix and notice, and this notation is a very common notation. I'm going to take row 1 and multiply it by 4. So let me write what that is right above row 1. So row 1, this is going to become 4. This is going to become -8. And this is going to become 4. And I'm going to add those individually down to this row. So I would have 4 and 4, which would be 0, -8, and 5, which is -3, 4 and 9, which is 13. And then don't forget our last one, which would just be 0 plus -9 is -9. So our new matrix that we actually get out of this, notice the first two columns, the first two rows, excuse me, are exactly what they were before. And this new row that I just defined by taking row 3 and adding a multiple of row 1 to it, got this. Now, Why did I do all of those addition and multiplication? Well, our strategy to solve these, and this will become more apparent in future sections, is I would love to get it where I have a value on this, on all the diagonal things, and I have zeros in everything below. I don't care what's above, but I just want zeros in everything below. So notice I have now made zeros in these first two spots. So all that's left is I want to make this spot a 0. Well, if I added the first row again down, it's going to change this 0 because that's going to be some multiple of 1 added 0. I don't like that. By the way, we don't add 0 multiples of 0. That just doesn't work. So instead, what we are going to do is let's add row 2. But how would you add row 2 down to row 3? Well, something that we can do first, notice that row 2, if we multiply by 1/2, which is that I can scale in a row, it changes it. The 0 times 1/2 is 0, 2 times 1/2 is 1, -8 times 1/2 is -4, and 8 times 1/2 is 4. And we get this. Now it's really nice because now we can be like, oh, wait, if I multiply this by a 3 and add it down, that's gonna make that go away. So we can do exactly that. So resetting my screen, if I had 3 times that row, it gives me this new matrix. Now, what does this mean? Well, if I took the system and I rewrote it as, so notice I just put in the x1, x2, and so forth. Notice this last line, now we have x3, it's equal to 3. We've already solved for one of our values. We can then plug that in into here, into this spot where we have x3, as well as up here. If I do that, notice I get x1 minus x2 plus 3 is equal to 0, and x2 minus 12 is equal to 4. We can now solve for x2 by adding 12 to both sides, and also by subtracting 3 from the first one, and I get this. So notice x2 is 16. Hey, wait, I can now plug that in here. I can take this value and plug it in. And I get x1 minus 32. So we can add 32 to both sides. I get 29, 16, 3. So my solution literally, sorry about that, I clicked the button one too many times, is 29, 16, 3. That is our solution right here. Where the first one is our x1, the second one is our x2, and the final one is our x3. So this is how we can solve a system of equations using matrices. All right, I'm going to pause the video just because this is getting a little long. I want you to come back and watch the other examples and help work through them.